Hi everyone, this is Hashwant. Today I will be presenting you my project for this course, that is isogeometric analysis with Kirchoff-Love shell elements. And before proceeding, let's discuss why do we need Kirchoff-Love shell elements, and why do we need isogeometric analysis for Kirchoff-Love shell elements. So usually most of the shells structures that are present in our engineering applications are in the range of thin and very thin. But we use Kirchoff-Love shell theory for analysis of these thin and very thin shells to get analytical solutions. But most of the commercial softwares avoid using Kirchoff-Love shell elements since they require C1 continuity between elements. Instead, they use Reisner-Millin elements, which require only C0 continuity between elements. Hence, it is difficult to use Kirchoff-Love shell elements for in regular finite element analysis. But in isogeometric analysis, we use knobs as the shape functions for both geometry as well as analysis, which allow for higher order continuities. Hence, Kirchoff-Love shell elements can be modeled using isogeometric analysis. And the main nonlinearities that we encounter are due to geometric nonlinearity that we will see further when we model Kirchoff-Love shell elements. So before proceeding further, let's have a brief introduction to B-splines. So B-splines are so any B-spline curve can be defined using three main ingredients that are: one is control points, and second thing is the degree of the curve that is denoted by P, and knot vector denoted by Z. And so there are different types of knot vectors which are categorized as uniform or non-uniform. Uniform if all the knot vectors are equally spaced, and they are and one good thing about B-splines is that they are C infinity continuous inside a knot span, that is between two knot elements, and CP -1 continuous at a single knot knot element. And in most of the cases we use open knot vectors, where in which case the first and last knots have a multiplicity of p plus 1, where P is the degree of the curve. And this is a formulation which we use to define B-spline elements. As we can see, from this we can deduce some important properties of B-spline basis functions. That is, they are local. That is, it is the bases are not are not equals to 0 only in certain region of knots, and they sum up to unity, and they are non-negative, and they are linearly independent. So using these B-spline basis functions, the knobs, curves, and surfaces are defined by the following formulas. And two things we need to keep in mind are the continuity and mesh refinement. So first, continuity, we have two types of continuity, that is geometric continuity and parametric continuity. Geometric continuity is when two curves meet at a single point and tangents are parallel. In parametric continuity, two curves meet at the same point and the tangents are not just parallel but also same in magnitude. So the mesh refinement is similar to that of finite elements, but here we introduce new knots, which is similar to H refinement, and by increasing the degree of the polynomial P, we get P refinement. So first we will deduce Love shell elements, Kirchoff-Love shell elements, and from there which are used for analysis. So the main assumptions behind Kirchoff-Love shell element is that the transverse shear deformation is neglected, and the normal vector to the mid surface remains normal even after deformation. So if we so the deformation u is defined as a difference between the position vector in deformed configuration minus the position vector at at the reference configuration, and we define covariant base vectors as tangents with respect to the both reference as well as current configuration, and we define covariant metric coefficients which are used in evaluating strains. So these are some of the mathematical definitions that we need for evaluating strains, and we use Green-Lagrange strain tensor, and so this using Kirchoff-Love elements, they have evaluated Green-Lagrange shear strain as having two parts. One is due to membrane action as well as a linear part which is due to bending. So so the constraint relationship that we use is a Saint Bernard's Kirchhoff material model. Here we have separated two parts of the second Piotrowski Kirchhoff stress into membrane as well as bending parts from the formula that we have used here. And so the weak form can be derived from the strong form by applying the directional derivative with respect to variation in displacement, variation in deformation, and from the weak form applying directional derivative with respect to change in deformation, we get the stiffness matrix. So this is a form of stiffness matrix that we use for the Kirchoff-Love shear elements. So the main algorithm of using isogeometric analysis is that we start with reading input data values and use connectivities, and this is similar to that we use in our regular finite element analysis, except that here the evaluation of basis functions and derivatives are with respect to B-spline functions. And for integration, we use Gauss quadrature rule. So the two problems that I wanted to study for this project is Timoshenko beam, that is a cantilever beam under parabolic load, and the second thing is a infinite plate with circular hole. So here we can see the boundary conditions as well as the loads on these two cases. So these two geometries I have generated using the knobs shear function as well as and then refined them to get mesh kind of shape. But unfortunately, I was not able to study the isogeometric analysis of these two cases, but I tried to find out the solution for these using for a linear elastic plates. So the results are matching close to that of the solutions found using analytical solutions. But the actual thing but the thing is that these are linear elastic plates and didn't use any Kirchoff-Love elements which carry non-linearity with them. So currently only simple problem of analysis of elastic plates is carried out, which is a linear analysis. But in future work, I'll be studying isogeometric analysis of Kirchoff-Love elements with for the above problems. Thank you.